We are third year undergraduate student of Visvesvaraya National Institute of Technology, Nagpur. This video shows our work on design and development of an EMG driven microcontroller based prosthetic leg. This project is completed under the able guidance of Professor K.M. Burchandi of Electronics and Communication Engineering Department. This project is given as an entry to Texas Instruments Innovation Challenge India Analog Design Contest 2014. Our project aims at providing prostheses for above-knee amputees, in which the important part is to acquire the EMG signals from the calf muscles of healthy leg and analyze them to provide the control signals to actuate the knee joint using a microcontroller. Our motivation behind this project is the fact that in India there are nearly 80 lakh people living with limb loss and around 6 lakh people in India require prosthetic leg every year. Around 70% of these are from rural areas. Being engineering students, it's our responsibility to develop the technology that can improve the life of disabled people. The drawback of the traditional prosthetic leg, which are in use, that they are designed mainly for below knee amputees. Also, the knee joints are not automated for prosthetic leg designed for above knee amputees. The other drawbacks are that the available ones are quite heavy and expensive enough that the people from rural area cannot afford it. In next part of the video, we present our solutions to the drawbacks of the traditional prosthetic leg.
Considering the drawbacks of traditional prosthetics, our aim was to develop a cost-effective prosthetic leg with an actuated knee that helps control basic motion tasks like walking, running, sitting on a chair, standing up, staying erect, etc. Now these are some of the parameters we considered while designing our prototype. The prosthetic leg should be sturdy and capable of functioning in harsh environmental conditions. It should be light in weight and strong enough to bear the weight of the amputee. It should have a proper transmission system providing sufficient speed and torque. We decided to use this worm and worm wheel arrangement as it provides a high reduction ratio which results in an increase in torque and a lower speed. Other advantages of using the worm and worm wheel arrangement include a longer life, a lower noise and a low cost versus torque ratio. The leg is made up of high strength plastic and we have used a high torque motor right here. To actuate our leg, we have made use of the electromyography signals from the healthy leg. Now what is electromyography? Surface electromyography is the technique for measuring levels of muscle activity. When a muscle contracts, electrical activity generated as action potentials propagates along the muscle fibers. We attached electrodes to the skin of the healthy leg, measured the muscle activity and graphed it as the person moves through various ranges of motion. Now why did we use electromyography? Using EMG makes it capable of variable speed walking. It also ensures that the prosthetic leg doesn't make any unnecessary movement.
As described earlier, we are using EMG signals for the automatic actuation of knee joint. We designed the circuit for recording EMG signal patterns and process them. This circuit also generates the control signal for the actuation. These are the AGCL type EMG surface electrodes which we are using to acquire EMG signals from the muscles. These electrodes are disposable and are very inexpensive, which are suitable for the low cost applications. These electrodes are connected to 3-lead differential electromyography sensor using 3.5 mm audio plug. This sensor measures the filtered and rectified electrical activity of a muscle, outputting 0 to Vs volts depending on the amount of activity in the selected muscle, where Vs signifies the voltage of power source. We can also adjust the gain using onboard potentiometer. This is Texas Instruments Stellaris EKLM4F120XL microcontroller launchpad. The output of EMG sensor is connected to analog pin of microcontroller. We here have used internal 12-bit ADC of the microcontroller to convert the analog voltage of output of sensor into corresponding 12-bit digital value. These digital values are then used for processing according to our algorithm to generate required control signals for the actuation of knee joint motor. This is Texas Instruments motor driver IC L293D. This IC gets control signal from the microcontroller and then it drives the motor according to it. This is high torque motor which we have used to actuate the knee joint. The power supply for the motor is given using 12 volt high current rating rechargeable battery. We have used two Texas Instruments voltage regulator ICs. This is IC7805, a 5 volt voltage regulator, and this is IC7905, a minus 5 volt voltage regulator. Using these two ICs and a voltage divider arrangement of the resistors, we have designed a constant voltage dual power supply for the sensor. We have used two 9 volt radio batteries for the dual power supply of the sensor. This is also a 7805 voltage regulator IC by Texas Instruments. This IC is used to give the regulated power supply to the launch pad. We tried to make our circuit as compact as possible so that it can fit on a small PCB. Our whole circuit and the power supply can be easily carried in a small bag, which makes it user friendly.
The key to achieve a successful EMG recording resides in understanding how to use and where to place the EMG electrodes. As the placement of the electrodes is very important, the optimal position of electrodes is found after performing several trials. In our project, we chose to take the EMG signal from the calf muscles of lower part of the healthy leg of an amputee. One electrode is placed in the middle of the calf muscle body, which is connected to the red cable snap connector. Second electrode is placed at the end of the muscle body, which is connected to the blue cable snap connector. Third electrode is placed on a bony or non-muscular part of the near calf muscle, which is connected to the black cable snap connector. For debugging purposes, we have a software program running on the computer which can record the EMG signals. For that, we send the digital values of signal from microcontroller to the computer serially, and software program running records and then plot these values in real time. We studied the normal walking gait of a human being. Normally, while walking, 70% weight is shifted alternately from one foot to another. The forward motion of the leg in the swing phase begins when the 70% of the body weight is shifted on the other. Therefore, it is important to detect this point at which the knee joint is to be actuated. For this purpose, we took several EMG signals recordings from the various muscles. We found that this point is distinctively described by calf muscles EMG signal patterns. So we chose to take the signals from calf muscles.
This video shows the EMG signals acquired from the calf muscles of the right leg. The peaks in the values of EMG signal represent the point when 70% weight is shifted on right foot. The acquired EMG patterns are analyzed by microcontroller, and when these peaks are detected by our algorithm, the knee joint of prosthetic is actuated.
This is the final setup to demonstrate our project. As we can see, the EMG electrodes are placed on the calf muscles of the right leg. This small package consists of battery for the power supply of the motor and the electronic circuit. We didn't have any amputee for the demonstration, therefore we have attached the prosthetic leg using a wooden plank to the thigh of this person. As we can see, the thigh motion is imparted to the prosthetic leg as well. It can be easily noted that when the person's weight is shifted on his right leg, the actuation of the knee joint of the prosthetic leg takes place.